So before we move on to the next part of chapter 10, I want to take a few minutes and work a few more problems with you that have to do with these hypothesis testing. I want to make sure that we really have this down before we move on. So specifically, the problems I'm working are in the Chapter 10 Excel workbook, and they're in the back of, or rather in the middle of the chapter. So if you have the printed textbook, they're on page 339. If you're looking at the online textbook, they're after section 10.1. And I'm going to start with question number 17. So it's titled Refrigerator Longevity, and you see that that is the worksheet that I have pulled up here. So I'd like for you to just go through this with me for a minute. So pause the video, see if you can get your book out, find page 339 or question 17 at the end of section 10.1, and let's look at this together. So in refrigerator longevity, in this problem, we're told a consumer advocate is researching the life between two different brands of refrigerators, brand A and brand B. He collects the data measured in years of the longevity of 40 refrigerators for both brand A and brand B. So these are independent random samples. So part A, first of all, asks us to specify the competing hypotheses to test whether the average life differs between the two brands. So let's just first of all write out what our hypotheses would be. Now, just for the sake of expediency, I'm not going to write it out exactly correctly with the subscripts and the muse and all of that, just because that's a little harder to enter. So I think you'll get the idea. So our null hypothesis, which I'm going to call H0, is that the mean of A minus the mean of B, so the mean lifespan of brand A minus the mean lifespan of brand B is equal to 0. So we're just testing to see if there's a difference between the lives. So we're testing if the lifespan is different. So this is be equal to 0. So this tells us, first of all, that this is going to be a two-tailed test. So then our alternative hypothesis is that the mean of A does not equal, I'm going to put a slash, does not equal the mean of brand B. So again, just wanted to type that out there for us. So then part B asks us to calculate the value of this test statistic and the p-value, assuming that the variance of brand A is 4.4 and the variance of brand B is 5.2. So in this problem, they give us the variances. The variances are known. So that's going to change what kind of tests we run. So let's go over here to, I'm in the data tab. I'm going to go over to data analysis. And because I know the variances, I'm going to choose the Z test down here to sample for means. Now I've already put the data in here once you run it the first time. So my variable, my A1 is, or my variable for 1 is A1 through A41. You can see I've got all the data highlighted there. And then for variable 2 range, it's B1 through B41, and you can see that we've got all that highlighted here. Now, because we know the mean difference is hypothesized to be 0, I entered 0. Since we know the variances of each one, I'm going to go ahead and enter those in. So I've just typed in variance for 1 for brand A is 4.4, and the variance for brand B is 5.2. Make sure that you enter the correct variance in the correct variable, however you've identified them. And then I did check that I have labels. We were asked to do this at a 5% significance level, so I set my alpha at 0.05, and I want my output range to be, let's do here in D4. So now I'm going to press OK. I'm going to make these windows a little bit larger so that we can see. So now notice it gives us the mean lifespan of brand A is 16.525 years, and for brand B is 17.25 years. Notice it says known variance because we entered those that we knew them. The hypothesized mean is 0. So my test statistic, my z-score, is a negative 1.4799. Now we could look this up in a z-table if we wanted to. But we don't have to because it gives us the p-value right here. Now remember, this is a two-tailed test, so I'm looking at the p-value for the two-tailed test. I'm going to highlight that, and so I can see that the p-value is 0.1389. So since the p-value is greater than 0.05, we cannot reject the null hypothesis. At a 5% significance level, we cannot conclude that the mean longevities or the mean lifespans of brands A and brands B are different. Okay. Now let's do another one. So let's look, if you're still on page 339 in the textbook, let's look at question 19 called different diets. And you'll notice that I've moved my Excel spreadsheet around and I'm now on the different diets worksheet here. And so this is telling us that according to a study published in the New England Journal of Medicine, overweight people on a low carbohydrate or Mediterranean diets lost more weight and got greater cardiovascular benefits than people on a conventional low-fat diet. That was reported in the Boston Globe, July 17th of 2008. A nutritionist wants to verify these results, and so they have documented the weight loss in pounds of 30 dieters on either a low-carb or Mediterranean diet, and those are listed here in column A, and then on a traditional low-fat diet listed here in column B. So first of all, we're asked to set up the hypothesis to test the claim that the mean weight loss for those on the low-carb diet is greater than the mean weight loss for those on the low-fat diet. So the test is hypothesizing that the low-carb dieters lose more weight than the low-fat dieters. So first of all, we need to set up our null hypothesis. So H0, our null hypothesis. So our hypothesis is that A, or the low-carb diet, is greater than B. But remember, we have to express this like in terms of 0. So really, we think that the mean of 1, or the low-carb diet, minus the mean of 2, or the low-fat diet, is less than or equal to 0. So in other words, if mean 1 is larger than mean 2, then this will be greater than 0. So our alternative hypothesis, remember what we're really testing, is that the mean of 1, the low-carb diet, is minus the mean of 2, which is the low-fat diet, is actually greater than 0. So sometimes I find it easier to start with the alternative to decide what it is I want to test, and then I can back into the null. So I want to see if the difference is greater for the low-carb diet. So I want to see if mean 1 minus mean 2 is a positive number, is greater than 0, then that tells me that the mean of the low-carb diet is significantly different than the mean of the low-fat diet. And so we're told to calculate the test statistic and the p-value, assuming that the population variances are equal. So they're unknown, but we're assuming that they're equal, and we're going to use, again, a 5% significance level. So I'm going to go over here to my data tab and click data analysis. And now, because I assume the equal variances, I don't know what they are, but I'm assuming that they're equal, I'm going to choose the t-test with 2 sample assuming equal variances. Now keep in mind that this is now a one-tailed test because I have a greater than or less than in the null hypothesis. So this is not a two-tailed test, it's a one-tailed test. So I'm going to click OK. So my input range for A for 1 is going to be A1 through A31, and we've got that highlighted. And for B, for variable 2, it's going to be B1 through B31. Again, our hypothesized mean difference is 0. I do have labels. My alpha is 0.05, and my output range, I'm going to put this here in D4. So now I'm going to click OK, and let's look at the data. So first of all, we can see that the mean weight loss for the low-carb diet or the Mediterranean diet is 9.77 pounds versus 6.28 pounds for the low-fat diet. Okay. So again, I just want to point that out. Now, we know that this is a difference, but is it statistically significant? I don't know. Let's go in and look. So our t-stat, our test statistic, is 7.58. Now, we could go look this up in the t-table and see if it's significant or not with 58 degrees of freedom, or we could just go down here to the p-value. Now, my p-value is, because this is a one-tailed test, I want to make sure I use the p for the one-tailed test. Now notice it's 1.59, but it's written in scientific notation, which means it's e to the negative 10, which means we need to move that decimal over and put like 10 zeros before that decimal. So, or really, I guess 9 zeros before that decimal. So this p-value is definitely less than 0.05. In fact, it's less than 0.01. So we could even go so far as to say that with 99% confidence or a 1% significance level, the data does suggest that individuals on a low-carb or Mediterranean diet lose more weight than their counterparts on a low-fat diet. So the data most definitely supports that observation. Now the last one that I want to look at with you is question 20 there on page 339, or in your Excel workbook. It's the tractor times worksheet. So here we're told that the production department of Greenside Corporation, who manufactures lawn equipment, has devised a new manual assembly method for its lawn tractors. It wishes to determine if it is reasonable to conclude that the mean assembly time of the new method is less than the mean assembly time of the old method. And so we've sampled 40 assembly times from tractors using the old method, and then 32 from tractors using the new method. So notice that our sample sizes aren't exactly the same, but they're fairly close. And so then we're given the data here below. So first of all, we need to set up the hypotheses to test the claim that the mean time of the new method, which we're going to identify as 2 because it's listed in column B, is less than the mean time of the old method. So again, I'm going to start with the alternative hypothesis because I find it sometimes a little easier to write that. So if I think that the mean of the new time, let's call that 2, is quicker, is smaller than the old time, then I think that mean 1 minus mean 2 will be less than 0. I think M1 is going to be greater. It's going to take longer under the old time. So that means M1 minus M2 would be less than, less than 0. Goodness gracious. I said it backwards, didn't I? Nope, I still said it backwards, didn't it? I still wrote it backwards. So I think that M1 minus M2 is going to be greater than 0. Sorry, I had to fix that there. I knew it didn't sound right because I think that the old times are longer than the new times. So I'm testing that mean 1 minus M2, so the larger number comes first in this case, would be greater than 0. So that means my null hypothesis, goodness, is that mean 1 minus mean 2, sorry about that, that mean 1 minus mean 2 is less than or equal to 0. Remember, your null is always the opposite of what you're testing of your alternative hypothesis. All right, so let's jump down here and run the data. So now because I'm told that the population variances are not equal, so I'm going to use the t-test assuming unequal variances. My range for variable 1 is A1 through A41. If we scroll all the way down here, we can see A1 through A41. And then my variable for range 2 is going to be B1 through B33. Okay. Now I'm hypothesizing that the mean difference is 0. I'm going to use my labels. And now let's look at this with a 10% confidence level. Let's just see what happens. So let's change this to 0.10. And I do want to change my output range. Let's put the output here in D5. And now I'm going to press OK. Now remember that this is a one-tailed test because it has a greater than or less than sign in the null hypothesis. So here we can see that for the old method, the mean time was 32.75, and for the new method, the mean time is 32.09. So slightly different, but not a whole bunch. But let's just check. So our t-stat, again, is 1.436, approximately rounded. So again, we could look that up in the t-table, or we could come down here and look at the p-value for a one-tailed test. Now, at a one-tailed test, we have a p-value of 0.077. So that is less than 0.1. So we can say at the 10% confidence level that the mean time of the new method is quicker than the mean time of the old method. However, if we were using a 95% confidence level, if we were using 0.05 as our significance level, we could not say that they were different. So they are different at the 90% confidence or a 10% significance level, but not at a 5% significance level. Do you see the difference there?